Sí, sí, sí. Víctor. Okay, good morning, everybody. Welcome to today's ISA colloquium. We have the pleasure to host this week Annette Ferguson from the Institute for Astronomy of the University of Edinburgh and the Royal Observatory of Edinburgh. So Annette is an expert in resolved stellar population in nearby galaxies, so a local group slightly farther out than the local group. And Annette is originally from Scotland, and she got her PhD at the Johns Hopkins University in Baltimore, and she moved to Cambridge, Groningen, and Garching for a postdoc position before getting a permanent in Edinburgh. So we welcome you today, and thank you for your talk.
Okay. I being heard loud and clear? No? Right. I have turned this on. Yeah. Better? Really? Sorry? I have to speak louder as well. Fine. Okay. Well, thanks very much for the introduction, and thanks very much for the invitation to be here this week. I've had a really, really nice few days. I've enjoyed my discussions with Karma and Matteo, and I've also really enjoyed the sun, because in Edinburgh we don't really see so much of that, and it's been beautifully sunny since I've been here, so that's been great, and it's been a really nice atmosphere to sit and get some work done, so I very much appreciate that. So my talk is going to be focusing on what we can learn about galaxy formation and evolution from studying the outskirts of fairly nearby galaxies, and by fairly nearby, the systems I'm going to be talking about are within our local group, or maybe out to about 5 megaparsecs away. So I thought I might tell you why I've been working, what my path has been to end up working on these kinds of issues. And it almost starts here. So at the last time, the only previous time I've ever been on Tenerife was in 1992, and I was a beginning PhD student then. And at that time, I was working on studying H2 regions in galaxies, massive star formation. And one of the current questions was whether or not you found H2 regions in the outskirts of disk galaxies. And so there was a fantastic IAC winter school organized in, I think it was Puerto de la Cruz, and there were some excellent lectures, and it was a brilliant couple of weeks on the social side as well. And I spent most of the 90s working on this question of young star formation in the outskirts of galaxies and finding good evidence for H2 regions out there. But by the end of the 90s, I started thinking about, okay, there's young stars there, but are there old stars there as well? And until that point, this was a question that hadn't received a lot of attention in the literature. And so that's why I got interested in looking at the older stellar populations that might reside in the outer regions of galaxies. And around that time, there was also renewed interest in trying to do this. The Sagittarius dwarf galaxy was discovered in the mid-90s, and within a few years of that, it was realized that it had spewed a whole stream of stars throughout the halo of our galaxy during its destructive path. So that also provided a motivation for trying to study these regions. And since, maybe the last 15 years, I think there's really been an explosion of interest in looking at the outskirts of galaxies. And there are various people here, like Nacho, that are also really active in this field and trying to work on many of the same problems that I'll be talking about today. So just a brief thank you to some of the people. These are postdocs and students that have contributed to the work I've been doing over the last 5 years or so, and you might recognize Edouard Bernard's name because he was a PhD student here, and he's been in Edinburgh now for the last 5 years. Okay, so how do galaxies form and evolve? This is the basic question that I'm hoping to be able to make progress on. And I think it's relevant to just remind ourselves that galaxies are actually really complicated systems. This is a schematic diagram of our Milky Way. And alone, there are 5 distinct stellar components here. There's the bulge, the thin disk, the thick disk, the stellar halo, and then globular clusters. Our best ideas about galaxy formation suggest that each one of those stellar components formed in a different way over a different time scale. So the question of when did a galaxy form is actually not a particularly well-posed question, because galaxies are really complex systems that are multi-component. And the way in which different bits of galaxies form is probably very different. So these days, there are computer simulations that can give us quite a lot of insight into these processes. And so I think the quest is really in looking at the nearest of galaxies, where we can try and attack the fine structure of galaxies with the greatest precision. So how do we think galaxies arise in the universe? Well, the main thing that models start off with is forming structure of some sort. And these are models that are quite well developed now. Probably everyone knows of the lambda CDM paradigm. The main ingredient in structure formation simulations are some kind of a cosmological model. So we want certain ingredients in the model, and that would be dark energy and dark matter and baryons. And we want some curvature for the universe, some spectrum of initial density fluctuations. And the initial conditions for these simulations are now really pretty well known, thanks to Planck and a variety of other experiments. And once you have a model and you can, with all these ingredients, then you let it evolve under the influence of only gravity and see what happens. So this is a snapshot from the Millennium simulation, which is, almost historical work at this stage. It was done 10 years ago, but it was one of the most impressive dark matter-only simulations of its time. And the first simulation to show this, but it's just one of the many, to show that structure in our universe grows hierarchically. So what that means is that the first dark matter halos that formed were small, and then these systems merged together and accreted other halos to grow over time. So there's this hierarchical build-up of mass. Now that's fine, that's dark matter only, and this is probably a picture that most people will not argue too strongly about these days, but what you will have a lot of arguments about is how do you actually get galaxies inside these dark matter halos. And the problem there is it depends on the baryonic physics. So how do you make stars form? How do those stars impact back to the interstellar medium? So the next steps of trying to get a galaxy inside a dark matter halo, we have a schematic picture of how we think this takes place. Baryons cool and collapse inside dark matter halos to form disks. And if they can preserve the initial angular momentum that they probably got from tidal torques in the early universe, then they can form with roughly the right size to match our Milky Way. So for a long time that was a problem in modeling disk galaxy formation. The disks that formed were far too small to be good matches to our Milky Way. But I think these days most people are quite happy that this problem is on the road to being solved, if not already solved. So once you have a gas disk, that gas will slowly start turning into stars. Stars throughout their lives, they evolve and then they die at in some way at the end of their lives. And throughout this process, they impact energy of various forms, as well as metals into the interstellar medium. And this feedback is one of the main uncertainties in modeling galaxy formation, along with the process of star formation itself. For massive galaxies, there's an additional feedback process that people are very concerned about, which is the feedback from active galactic nuclei. That's probably not so important in galaxies of Milky Way size and lower, but in giant elliptical galaxies, this AGN feedback may be another way that either inhibits or triggers star formation to occur at some point in a galaxy's lifetime. So stars start to form inside the dark matter halos and the disks, and they start to input feedback into the gas, and that may trigger or inhibit star formation. And while this is going on, the other process that's happening is that galaxies are continuing to grow via merging and accreting other small systems. Most of this activity is expected to occur early on, but there's certainly believed to be trails of this process even occurring at the present epoch. So with that basic picture in mind, you might wonder why we can't just then go off and construct models that model how our Milky Way would have arisen from the earliest times to today and have our model in place. And as I said, the key issue here is understanding the feedback and the star formation. And just to emphasize how crucial this really is, this is a paper that was written a few years ago by Scannapieco et al. There are 13 different model galaxies shown here. There's a face-on view and an edge-on view, and these are the stellar distributions of the galaxies that are shown. Now, in these 13 cases, the initial conditions were the same. They were all drawn from the same starting point, and then they were evolved by 13 different simulation groups using their best prescriptions for star formation and feedback at that time. So the end result is what you see, and none of these systems really look the same. They all have slightly different sizes, different extents, different morphologies, different bulge to disk ratios. And as I said, the assembly histories of the halos are identical in all cases, and the initial conditions are identical. So what's causing this difference is the way that the baryonic physics is being implemented. So this is the major stumbling block with purely modeling, trying to understand galaxy formation from a simulation point of view, is that these processes right now are too poorly constrained to give unique predictions on what galaxies should look like. So I think it's a fantastic era to be doing observational work in galaxies, and precision observations are really key because they'll allow us to try and distinguish between which star formation and feedback processes actually are producing systems that resemble real galaxies around us in the nearby universe. So what are some of the specific questions that we might hope to address with observations of nearby galaxies? And in particular with observations of their outer regions. So one of them is about the way in which disks grow over time. And this is a long-standing issue. Do disks grow inside out, outside in? Do the stars all start forming at roughly the same time? And in the literature, you'll find different predictions. If you look at this line here, this is from Abadi et al. 10 years or so ago. This is their mean age as a function of radius. It's pretty flat. Here's another set of simulations by Egertz et al. And here are their predictions for the mean age. This is the halo out here, so that's not so relevant, but they have strong age gradients. So you would think, why can't we just go out and directly measure that in the most precise way possible using resolved stellar populations? So that's one of the questions that I think we can make progress on. The other question is the degree to which galaxies grow by merging and accreting systems in the recent past. So these are simulations by Cooper et al. These are star particles that are tagged onto a dark matter simulation. It's 6 different Milky Way realizations that are shown here. And what you can see is the stellar structure that's predicted in their outer regions for these 6 halos that in the end look like our Milky Way in terms of global properties. So you'll see that in all cases, the morphology is irregular at large radius. What you might not be able to see, but I'll point out, is the surface brightnesses of this debris that we expect to see in the outskirts of galaxies. So red up here corresponds to about 1% of the sky, so that's maybe a V magnitude of about 27 or so. So that's red. That's the very central part here. The blue, which is probably what your eye will be drawn to, corresponds to about 0.01% of sky. So that's a V magnitude of about 32, right? So that's really pretty extreme. So unfortunately, to test these kinds of predictions in detail, we need to be able to image galaxies to extremely faint depths, and that's where the challenge really lies in this work. The other thing you might notice is that even although the end galaxy in all 6 cases kind of looks like the Milky Way in terms of its bulge to disk ratio and its rotation speed and growth properties like that, the halo structure in all cases is rather different, and that reflects the stochastic nature of the accretion process in a hierarchical universe. So even galaxies of roughly the same mass accrete different things at different points in their lifetime, and depending on what they accrete, they will show different kinds of patterns in their halo. So whether they accrete slightly more massive objects, low mass objects, objects on radial orbits, objects on tangential orbits, and exactly when these accretions occurred lead to the different kinds of behaviors that you see here. Concerning the substructure, another question is really just the amount of substructure that we see around galaxies. So returning again to what some ideas from that come from simulations, in cases where galaxies accreted most of their material very early on, in this case more than 12 gigayears ago, we would expect most of the accreted material to lie quite near to the galaxy center, maybe extending only a few tens of kiloparsecs across. In systems where the galaxy accreted most of its material more than 8 gigayears ago, we'd see a more extended system, and likewise, with more recent accretions, we would see more substructure and even some intact satellites still orbiting within the halo. So if we were able to view galaxies with these ultra deep glasses on and see these really low surface brightness levels, we would be able to go some way in testing whether the models that are out there right now actually make sense. And then this is just another idea based on surface brightness breaks at the point in galaxies where stars that form in situ, which is in the inner regions here, get overwhelmed by stars that are accreted. And this surface brightness break, which you can see in these 6 panels, these are panels that illustrate that are bins of stellar mass. So the Milky Way, I think, is in, I think it's in this panel here. Can't really read. Yeah, the Milky Way is actually going to be in this panel, isn't it? So you can see that the break in the surface brightness profile is predicted to change as one goes to higher stellar masses. And down here, this is the realm of CD galaxies and galaxy clusters, where the prediction is that almost all stars in CD galaxies have come from cannibalized galaxies of some sort. So if we had big samples, we could construct surface brightness profiles to these faint limits, look for these breaks, and test whether there really is a dependence on a stellar mass or not. So some of the key questions, I think, that we can really start to tackle with observations of nearby galaxies are outlined here. How common is stellar substructure at large radii in galaxies? So how often do we see these tidal stream features? What kinds of accretions occur, and when do they occur? How common are smooth stellar halos around galaxies? So without the tidal debris, just nice extended, classical old halos. And what are the properties of those halos? What are their radial profiles? What are the metallicities of the components? What's the role of in situ star formation versus accreted star formation in building up galaxies as a range of mass? What's the star formation history in the outer parts of disks? Do we see signatures of inside out or outside in growth? And also, what's the relationship between stars in the extended parts of galaxies and star clusters in these regions? Did they form together? Did they come in? Were they brought into galaxies together? What are their origins? So there's a great deal of work going on all these questions right now. I'm just going to try and say a few words about certainly the first two, and if there's time, a little bit about the third one as well. So start off with how ubiquitous is tidal debris around galaxies. So many of you may have seen beautiful pictures like this in the literature or in talks. This is a compilation by David Martinez Delgado. Every single one of these galaxies shows something weird going on in the outer regions. And this is a similar compilation that's been recently published by Pierre-Alain Duc from the Atlas 3D collaboration, showing galaxies in the Virgo cluster that show also great amounts of substructure in their outer regions. So you might be led to believe that all galaxies kind of look like this, but actually it's not really true. Most of the galaxies here were specially selected. They were known for many years to have something unique going on in their outer regions, but these images reveal that something in much more detail than had previously been seen. This is a map from the PANDAS survey of M31, which I may say a little bit more about later. To make this one image took about 400 hours of telescope time on CFHT. So there's no other galaxy in the universe, with the exception of the Milky Way, that's had that much observing time spent on it, probably. So, you know, even if M31 looks like this, that doesn't really tell us that all galaxies look like this. So to try and get a handle on this question, I did a project with Bob Abraham in Toronto and one of his PhD students, Adam Atkinson. And what we did was we took some of the deepest wide field survey data available at the time, a few years ago, which was the Canada, France, Hawaii survey, the wide survey that had been conducted with the telescope, the Legacy survey, and that covered about 170 square degrees on the sky. So a sizable area, but the important thing was it was also quite a deep survey. So it gave us a chance to try and study the faint outer structures of a statistical sample of galaxies and address the question of how often do we see something bizarre going on in their outer regions. So there was a lot of supplementary data available for this survey, and we were able to make pretty well-defined cuts on redshift. So we were examining a sample of galaxies that lay in a redshift range from 0.04 to 0.2 and were brighter than a certain magnitude. And so that gave us a sample of about 1,800 galaxies. These galaxies were visually inspected, largely by the PhD student on the project, but also a little bit by Bob and myself, which was fun. And what we did was classify the systems into different confidence categories. So confidence category 4 meant that we were absolutely convinced there was something unusual in the outskirts of a galaxy. Confidence class 3 was we were 75% sure that there was something there. Confidence class 0, we were convinced there was absolutely nothing there. So you can get the drift. And in classifying features, we also divided them into 6 categories. So when we saw something, we tried to decide which one of 6 categories best described that feature that we saw. And so we had systems that were arms, shells, linear features. Here's the linear feature. Stream, here's the stream down here. Fan, just sort of diffuse bits of material, and diffuse was its own category when it was just really hard to decide how to morphologically categorize the emission. So that's what we did. And so what did we find? Well, surprisingly, or maybe not, we found that only 12% of the sample of 1,800 galaxies definitely showed tidal features in their outer regions. And if we included confidence class 3 in this, which is systems where we felt there was a 75% chance that we were seeing something interesting, then that number rose to 18%. But still, even between confidence class 4 and 3, that's only 1 in 5 galaxies showed some interesting tidal debris in their outer regions. So these histograms really just show that. We were able to divide our sample into blue and red. So this panel is just lumping everything together here. This is confidence class 4, 3, 2, 0. And by far most of our galaxies, we were pretty sure there was nothing interesting going on in their outer regions. This panel just shows exactly the same information, only coded into red and blue galaxies. And something that's quite interesting is that in the systems where we were sure we were seeing some tidal debris, it was almost always a red galaxy around which we saw this, as opposed to a blue one. Yeah. Right. So the surface brightness limit, I'm going to say something about that in a second for the CFHT survey. For the images that I showed you here, are you asking about the surface brightnesses here? Right, well, I'm going to get to that in a minute. So just wait. So, right, so in any case, as I was saying, in the cases where there did seem to be debris, interestingly, it tended to be around elliptical galaxies as opposed to spirals. So, as Josephine has just asked, is this as expected or not? And unfortunately, we're really just touching the limit of where things start to get interesting with this work. So this is a plot taken from one of these simulations that I was discussing earlier. Each line indicates a different galaxy that was simulated, and what you have is a plot of the number of features brighter than a given surface brightness level versus that surface brightness level for these 11 simulated halos. The CFHT-LS survey, even although it's one of the deepest large galaxy surveys that's been done to date, its surface brightness limit is 27.7. So it's just up here. So according to these simulations, which admittedly are full of uncertainties about how you turn dark matter particles into stars, but putting that aside for now, these simulations suggest that actually only a handful of galaxies should show some debris above that limit. So we can't say anything too interesting on the basis of the work that we've carried out yet, simply that to the surface brightness level that we've surveyed, 1 in 5 galaxies show something, the rest of them don't seem to show any tidal debris at all. But looking at this plot suggests that if you're able to go even a little bit deeper, galaxies should start to uniformly look much more interesting. So how do we go about imaging galaxies even deeper than the survey that I've just discussed? Well, there are various ways that people have now been pursuing to study galaxies to superfaint depths. One of them is stacking, and here's an example of that by Tal and Van Dokkum. They've stacked 42,000 luminous red galaxies in the Sloan Digital Sky Survey, and they have beautiful surface brightness profiles in different photometric bands, and if you can read the axes here, this is 30 magnitudes per square arc second, and this is 100 kiloparsecs. So through stacking enormous samples of shallow survey data, one can obtain really impressive limits about the profile behavior of galaxies. There's some drawbacks to this kind of approach, even although it does attain the surface brightness levels of interest. It's technically non-trivial to do this stacking. When you stack, obviously you lose variance, and variance is one of the key predictions of lambda CDM models. We expect galaxies of a given mass to actually show different kinds of behaviors, and it would be great to be able to quantify that in some way. When you stack systems together, you lose all that information about individual systems. You're merely collapsing everything into a single profile. And furthermore, it's integrated light, and so it doesn't give you the constraining power that resolved stellar populations does in understanding the age and the metallicity mix of the constituent populations. So the way that, stacking, I think, is a really, really important way to pursue these questions. But the alternative way, which is the way my collaborators and I have been approaching this, is through use of resolved stellar populations. And I'm sure people here at the IAC do not need to have an introduction to what this is, but it's a simulated color magnitude diagram from a paper of Antonio and Karma 10 years ago now. It shows what you would expect for a color magnitude diagram from a stellar population that was forming with a constant star formation history, and the different colors here reflect different ages. And the approach that we've been using to studying galaxies at faint surface brightness levels is to use color magnitude information, and basically to count stars above a given magnitude that we see in certain regions of a color magnitude diagram, and translate that star count information into a surface brightness. So how does this work in practice? Well, here's the tip of the red giant branch. So that's more or less a fixed level for stellar populations. If we're doing ground-based work within the local group, it's quite typical to be able to image galaxies to about 3 magnitudes below the tip of the red giant branch with a big telescope. So you will have 3 magnitudes of RGB to work with. Not much in the way of young stars. Young stars are less important for the kind of questions that I'm talking about, which have to do with how galaxies have assembled over many giga-year timescales. So it's really the older populations here that are of most interest. If we want to push this kind of work beyond the local group, but out into the local volume, a reasonable limit that we've been able to achieve is about 2 magnitudes below the RGB tip with 8-meter class telescopes. So you've got that much of the RGB to work with. And just for reference, with HST, we can go all the way down to the oldest main sequence turn-offs. So what do? Well, basically by counting red giant branch stars and knowing what their luminosities are and making corrections for the stellar populations that we don't detect, we can translate the star counts into surface brightnesses. So, a typical number is this middle one here, something like about 1,000 RGB stars per square degree. It's a sizable population of stars, shouldn't have too many troubles detecting those. Translates into about 32 magnitudes per square arc second. So that already gets you quite a lot deeper than these integrated light analyses that I discussed earlier. So these are the results that we've obtained doing this work on M31. And as I said before, these maps have required about 400 hours of construction. Here you have M31, M33 down here. This is a cut on metal poor RGB stars, so the bluer RGB stars, these are the metal rich ones. And we're roughly spanning about 300 to 400 kiloparsecs on the side. So these maps are pretty unprecedented for any galaxy in terms of the surface brightness limit and the scale that they show. And you can see all kinds of interesting debris features. And in fact, there's a morphological change in the debris as you go from the metal poor to the metal rich. But one feature that does stand out in both of these maps is the giant stellar stream that was discovered in 2001 by our group, which indicates an ongoing accretion event that's happening in M31 right now. So there's a fairly massive satellite, seems to be heading straight for the center of the galaxy, though it's actually already impacted the center of the galaxy. But unfortunately, we can't really get this quality. There's also M33's got some surface brightness extensions going on around it. And here's the dwarf satellite pair up here, 147 and 185. And we've discovered a giant stream coming off NGC 147 as well. Data of this quality, as I said, it's impossible right now to routinely obtain this for more than the 2 galaxies that we already have. So what can we do? Well, we can try and go beyond the local group with more limited surveys. So what are some of the challenges that this work brings up? Well, one is depth. Now, I told you that the typical limit within the local group, beyond the local group right now, is a couple of magnitudes below the TRGB with an 8-meter. This is what difference that's likely to have on how a galaxy appears. So these are maps that I've made using the PANDAS data. and imposing different cuts on the RGB. So if you only had data that went 1 magnitude below the RGB, that's what M31 would look like. It's still kind of interesting. There's still sort of a lump over here, and there's some distortion over here. But it really doesn't look anything like what it looks like if you can go 3.5 magnitudes below the TRGB. So again, there's this great sensitivity to depth. Typical beyond the local group surveys are going to achieve this kind of depth, which is still interesting, but clearly isn't revealing the full extent of the debris that's out there. So that's a caveat that we have to keep in mind. The other main challenge of doing this work beyond the local group is to do with the contaminating populations that you find in the color magnitude diagram. So this is a system that's at 3 megaparsecs, NGC2403. This is its stellar color magnitude diagram, so sources that we detected and classified as point-like. This is sources here. Sorry, I think, yeah, these are the same color magnitude diagrams. In this case, we've just drawn on different population boxes that separate out RGB stars and AGB and main sequence. This is taken from the same data set. What's shown here are sources that we detected to be slightly extended, so they were galaxies. But you can see that this looks a great deal like this. The main difference is that this sequence, the primary sequence here, is slightly bluer than it is here. But as well as resolved galaxies, in our CCD frames, there's going to be literally thousands of unresolved galaxies, background galaxies that are so far away that they appear as point sources in our catalogues. So one of the challenges is to try to take this color magnitude diagram and sort out what's a genuine star here and what's an unresolved star that would, have a color magnitude diagram that would look something like this. And in addition to that, there's also Milky Way foreground populations that contaminate many of the regions of these CMDs as well. So this remains one of the biggest challenges, which is why using the Hubble Space Telescope is great, because you can do star-galaxy separation much better there. But the problem with the Hubble Space Telescope is that it's a tiny, tiny little field of view. It's about the size of this laser point at the distance of M31. So you can see that if you were just to take the Hubble and point at any random bit in the halo of M31, you've actually no idea what you would be landing on or what you would be measuring, whether you would be measuring a tidal stream or smooth halo. So the Hubble Space Telescope's not really the best way to go about doing this work in the local universe. So what's the kind of results that we've been deriving? Well, there are three systems that I'll just quickly show you some results from. M81, which is a famous system in the north. It's at almost 4 megaparsecs, NGC2403 at 3, and SENE in the south, which is at almost 4 megaparsecs. The telescopes we've been using are at Subaru in the north with SuprimeCam, although we now have a program using HyperSuprimeCam to do a large area around M81. And in the south, we've been using VMOS on the VLT. These galaxies are reasonably far away, and even using wide field telescopes in the ground, we can't do the kind of contiguous large-scale mapping that we've been able to do in M31 and M33, but we're still able to cover significant areas on the sky around these systems. So here's surface brightness profiles for M81 and NGC2403 that we've constructed using resolved star counts in their inner regions and diffuse light in the very central regions where crowding inhibits the detection of individual stars. And just to point out, so we're reaching impressive limits. M81, this is a surface brightness profile. It actually, at the edge of our data, it's still quite bright. It's about 28 magnitudes per square arc second. But, if it was fainter, I think that we would have been able to detect it. It's just got quite a bright envelope. And NGC2403, we've been able to reach surface brightnesses that correspond to about 32 magnitudes per square arc second. So these are the limits that others have achieved through stacking of thousands of systems. We've been able to achieve these limits in individual galaxies through resolved stars. What you might also see is that in both systems, the profiles change in their outer regions. They become flatter. So they follow the usual exponential decline in the inner region, and then they flatten. We don't have good constraints yet on what's happening at that flattening, whether it's the transition to a stellar halo or the transition to an extended disk of some sort. And unfortunately, these systems are far enough away that we can't get kinematics of the stars yet, even with an 8-meter telescope, to know whether stars in these flat envelopes are rotating or whether they're pressure supported. So we've also been doing work on Sen-A, and I'll just quickly flag, this is the surface brightness profile on Sen-A. This is the black points are the major axis, and the cyan points are the minor axis. And the main thing to note is there's some uncertainties in the background subtraction here, but the main thing is that even in Centaurus A, out at about 70 kiloparsecs, we also see a flattening in the surface brightness profile. So Sen-A is a very different galaxy type to the other two that are spirals. This is an S0, but it still seems to show this flattened envelope around it. So what's going on here? Well, I would summarize by saying that we believe bright tidal debris around galaxies is quite rare. Maybe 1 in 5 galaxies shows something like that. But these extended envelopes seem to be ubiquitous in the admittedly very small sample that we've looked at so far beyond the local group. It's also there in M31 and M33. These components contain maybe a few % of the light. We know something about the metallicities of these outer envelopes because we have color magnitude diagrams for the stars, so we can fit models to the red giant branch. And they're fairly metal-rich, so metallicities of about 1/10 of solar. So that's not the extremely metal-poor metallicities that you might expect for a stellar halo. Nonetheless, they're more metal-poor than what you would expect for the inner parts of the disk. So exactly what's going on with these envelopes, I think, remains to be discovered, but I think we can claim that they're certainly there in most cases that we've looked at so far. And hopefully additional data will help us constrain in more detail what these envelopes really are. So I think I was going to say something about M31's inner halo. I'm going to skip that. I'm going to summarize, and then I want to say a little bit about where I think this field is going to be going next. So that's basically, I think that's more or less just summarizing what I have already said. So what is the future for this kind of work? I've told you that thus far it's been quite painstaking work. We're able to study small samples of galaxies that require a lot of time on 8-meter class telescopes. So we're still not at the point where, I'd argued initially we would like representative samples of galaxies and we could survey their stellar outskirts to super faint depths, and we could say something interesting about the frequency of debris and the properties of the debris and the halo profiles. So at this moment in time, we're still quite far away from doing that kind of science. And my personal view is that things are going to stay more or less like this. We'll be able to chip away at individual galaxies over the next 5 years, but the real step forward will come with 2 missions that will come online in about 5 years from now. One of them is LSST, which you may well have had talks here about already. It's a 6.5-meter telescope. It's an American-led project. It'll see first light in 2022. It's going to do a big survey of about 18,000 square degrees. And if you're interested in transient and multi-epoch science, this is going to be a fantastic facility for you. What I'm interested in is the fact it's a big telescope, it's got good image quality, it's going to be on a great site, and it's going to reach faint depths. And I'll show you in a minute what that will translate into. Euclid is a European satellite, and it will launch hopefully in 2020. It's a small telescope, 1.2 meter, but it's going to be in space. It's going to have a big field of view, roughly 1 square degree, and it's doing a 6-year survey of something like 20 square degrees of the sky as well. And it also will reach interesting limits, not quite as deep as LSST, but what it does have going for it is it's going to deliver HST quality imaging over 20,000 square degrees of the sky. So So that's going to be pretty amazing. Now, Euclid, unfortunately, has some unusual filters going on, in that it has one very broad optical filter that extends from about 5,000 or 6,000 angstroms up to 9,000 angstroms. So completely unlike the kind of filters that most people are used to working with. And then it has 2 infrared, it's J and H. So what will we be able to do with LSST and Euclid? Well, this is the pandas image of M31 that I told you has taken us about 400 hours to obtain. So LSST will give us a picture like that for every galaxy within 3 megaparsecs. So there are many tens of galaxies that fall within that volume. So I think LSST will be remarkable for improving, giving us pandas depth images for a good sample of galaxies. Yes? This is stacked. Yeah. Yeah. End of survey. So it will give pandas depth for every galaxy within 3 megaparsecs. We started off the pandas work actually on the INT 15 years ago, and we did an INT wide field camera survey of M31, and that was what that looked like. Still see a lot of stuff here, even although pandas has revealed what's going on in the outer halo. LSST final will give us an INT view of every galaxy within 5 megaparsecs, so it will push the volume out even further. So even although it won't give us pandas depth, it will give us INT view. And going out to 5 megaparsecs is actually quite important because it brings in a range of other galaxy types that don't reside within our very local volume. Euclid, on the other hand, will give us good views of galaxies as well, not quite as deep as either of these, but certainly deeper than anything that we have right now. Euclid will be an excellent way to improve on the study that I discussed at the start with the CFH-TLS, because it will give really exquisite, deep imagery for a large sample of galaxies where we can look for tidal features in their outer regions. But Euclid will also have this high-resolution capability going on, which means that it should be able to lead to the identification of lots of globular star clusters in the outskirts of galaxies, because they'll appear resolved in HST depth imagery. But it will also give us color magnitude diagrams that we can work with for many systems as well. So as a taster of what may well come from these surveys, this is just some of our more recent, as of yet unpublished work on M81. I previously showed you some analysis that we had from this little region here that we observed with Subaru SuprimeCam several years ago. Since then, we've now mapped out this region here. So this is M81, M82. This is the gas image of Yun et al. That was published in the early 90s, showing that there was a tidal interaction going on here and there was gas everywhere. And back at that time, people said, well, you would never know that from looking at the optical image. And with the Subaru image images that we've now obtained, indeed you would know it. If you look deep enough in the optical, you can see this giant tidal stream that's linking N81 and N82. So, as I said, hopefully with these future facilities, we can start to build up these sorts of views for a sizable part of the local universe. So I'll stop there. Thank you.
Thank you very much. We have time for questions.
So, beautiful talk and really impressive results, and the way you have described where the future is going. But I'm puzzled by this result that if you try to find galaxies with tidal features which are obvious, most of them are red rather than blue. And I have this naive view that, blue are active galaxies, so they are forming stars which are brighter, and so it should be simpler for us to detect stars around galaxies if they are young, and so in blue galaxies. Could you comment on that? Why this happened?
Yeah, I mean, I think that result is kind of puzzling, but it's not totally out of line with what's appeared in the literature. See, yeah, this slide here. I'm not sure I would agree that it should necessarily be easier to detect. I mean, my naive view is that it should be the same, whether you want to find tidal debris around red or blue galaxies, because the tidal debris is created by whatever fell in, right? So that could be anything. That might not have a dependence on the host galaxy. I don't know. So I think in terms of looking for the features, possibly it's harder in the blue galaxies because they have spiral arms, and there might be some confusion with trying to identify what's a spiral arm and what's a tidal feature. The fact that we found that red galaxies seem to have more stuff is actually in line with studies that Van Dokkum has done. So there's, I don't know if you're familiar with his 2005 paper, and he got a tiny little bit deeper than us, maybe 28 instead of 27.7. He found a tidal debris fraction for just red galaxies of 70%, which is way off what we found, and it's way off what almost every study in between has found. But certainly, if it's correct, it does push things in the direction that the red galaxies, for some reason, are the ones that have recently accreted stuff.
Could it be due to the fact that these red galaxies are at the center of clusters? I mean, these are very massive galaxies, and so you expect that, I mean, all these satellite accretion process is far more effective at the center of...
Yeah, I think, well, actually it's interesting because the studies, some of the more recent studies that have been done have actually looked at galaxies in the cluster environment, and they've found even lower fractions of tidal debris than in the field. The idea there is that in a cluster environment, because galaxies have a larger velocity dispersion, interactions are less likely. Well, these minor interactions, so the tidal debris fractions in clusters seem to be lower than they are in the field. So I don't know, it's a puzzle, and I think more data are clearly needed here to understand this difference between the red and the blue galaxies.
Yeah, just to comment on his previous question, I think the reason is what you were suggesting about the mass. I mean, when you make a magnitude limit cut, 70 magnitudes or so in R band, then by definition the reddest galaxies are going to be more massive. And you know that there is such a prediction that most massive your galaxies, your gravitational potential is deeper, so then you have more, your abilities, I mean, your probability of having larger accretion is larger too. So this is also in the simulation. The most massive galaxies have more material accreted. So I think that what we are observing here is just, I mean, if you were repeating this exercise, instead of selecting in the R band, just selecting in stellar mass, for instance, then you probably would see the
you see a different trend.
Yeah, the difference. I think so.
Have you in fact made this as a function of mass?
So yes, we have looked at something as a function of stellar mass, but not this. What we looked at actually was the incidence of different kinds of. So we looked at the incidence of these different kinds of six different kinds of features as a function of stellar mass. That's what we looked at to see if you found one morphology of feature more often in a high mass galaxy than in a low mass galaxy. And I don't have that slide in this presentation, but we identified a few classes. I think, yeah, I'm not going to remember. I think maybe shells and streams seem to be more commonly seen around the high mass galaxies than the low mass galaxies. But our sample doesn't span a huge range in stellar mass. Yeah, I think it's barely a factor of 10. So there's not a huge deal of sensitivity to that within the sample.
Right. I was actually going to ask a more technical question for once, which is there a nice engineering reason why we've got this unorthodox filter on Euclid?
Sorry,
the unorthodox filter on Euclid. Is there a nice technical reason for why that's been put there?
The reason is because Euclid, well, I believe the reason is Euclid's a dark energy mission. So the survey design is driven by the needs of the dark energy experiments. And what they need are precise shapes of galaxies in the optical, and they don't really care about photometric information. So a nice broad filter, such as is being used, gives maximum information about the shape of a galaxy in minimum time, and they don't need the color information.
One of the problems of lambda CDM models in general, a well-known problem, is the lack of satellites, observed satellites. One of the reasons proposed for this is that they've been eaten by the big galaxies previously. The fact that we don't, or you don't find, or one doesn't find very much tidal stuff around, does that have any bearing on this?
So
it would imply that that hasn't happened.
Well, the missing satellite problem is really for the very low mass. Well, it depends. It can also be the moderate mass stuff, but predominantly it's the very low mass stuff. So it's like the dwarf toroidals around the Milky Way. So the brightness of debris depends on many things, but it partly depends on the mass of the galaxy that has been disrupted. And if you have something like a local group dwarf toroidal, something like, I don't know, sextans or, lower, the debris that you would expect from that is going to be super faint, well below the limits that we've been able to detect anywhere except possibly M31. And M31, the PANDAS survey has led to the discovery of, I don't know, something like 10 or so new dwarf galaxies. And as of now, there's no clear signs that any of them are being... We haven't been able to detect tidal debris from any of them yet. So some of them may well be in the process of being disrupted as they orbit around M31, but the debris is so faint that even with the PANDAS survey, we haven't actually seen signs of that. So I don't think we can make any strong claims there based on the data that's in hand.
And now I have a question before it was a comment. So related to NGC 2403, where you see the excess of light in the outer region, where you say that you mentioned that you have doubts where this is a external disk or the emergency of a stellar halo.
Yeah.
So in terms of super brightness, it really looks like a stellar halo. So, but I mean, I was wondering whether you are able to explore the morphology of that feature in just seeing whether this is elongated like the disk or whether it's more roundish.
Right. Yeah, absolutely. So I don't think you can say something like in terms of surface brightness, it looks like the halo. Cooper doesn't have any disks, right? Cooper doesn't have any disks in his simulations. He doesn't. Yeah. Yes. Yeah.
So where they saw the super brightness profile for Milky Way, that one.
There we go.
No, the one with the super brightness profile.
Oh.
That one. Yeah, that one. The first panel on the. So the first part, you see the blue line. It's an exponential like, and then at around what they call 5. So you see the vertical axis where the 5 is. This is equivalent to 30 magnitudes per square second.
Right.
Which is where the break is.
Right, but so in these simulations,
this is the disk.
Yeah. So there's no such thing as a disk and a halo. Yeah. There's in situ and accreted.
But I mean,
okay. So there's in situ and accreted. There's no components.
No. So you see, in situ is the dashed line, and it's just behind the blue.
Yeah.
So this is the in situ.
So here it goes. Do you think it ends here? No, it keeps going. It keeps
exactly.
Going.
It's going. But I mean,
it goes all the way down. It's just it gets dominated by the halo.
Exactly.
So at a given surface brightness, you have a contribution from multiple components in a galaxy. But anyway, to get back to the point on NGC 243, yes, we've been able to look at the shape of the envelope, and actually it looks consistent with the ellipticity of the disk. So, yeah, it doesn't look round, it looks more elongated. But it's hard because the signal is very low, so you can't put very strong constraints on that.
Okay. Last question.
Thank you. In the introduction, you showed how important were the observations in order to put constraints in the models and simulation that we know have a number of parameters that need to be constrained, right? However, during your talk, you have been shown the need for going to deep images to get to low surface brightness, the outskirts of the galaxies. But you have shown a variety of galaxies which are very wide. I mean, you have nearly early type to late type, big things and small ones. So my question is that, do you think that without constraining the targets that are going to be measured and being used for the models, for constraining the models, do you think that we are going to get into a big number of observables that still can be interpreted in a very diverse way?
Yeah.
In particular, if you have very late type galaxies, you put 2403. So it's a galaxy which is filled with these, your H2 regions, your all H2 regions, right? So there, a number of things are happening still now, that this is almost being constructed now, and the number of features that you are going to see in the outskirts are going to be contaminated by a number of other things which are not simulated in the models. So my question is that, do you think that for the sort of work that you are doing and you are proposing would be sensible, I don't know, to restrict the sample if we want to put real constraint in the models, or all possible galaxies are useful?
So my take on that is that all possible galaxies are useful and required. And I get your point that right now we've got a very small sample that we've been able to look at, and they have diverse properties. And so right now I would not feel confident about using any one particular galaxy as a reason to go and challenge a model. You can't do that. But I think it's very important to look at as many, that's why Euclid and LSST will really, I think, really make an impact on this issue, because they will give us big statistical samples, and you can imagine that averaging over many galaxies, you will get rid of the sort of behavior that's specific to any one galaxy, like if it's, having above average star formation or something like that. If you have big samples of galaxies, you'll average over that and you'll see what are representative properties. In NGC 2403, the interesting envelope stuff is out beyond 20 kiloparsecs. All the star formation that's taking place right now is, it's within 12 kiloparsecs. So there are no H2 regions anywhere where, well, not that I'm aware of, anywhere where we're looking, which go, from sort of out to almost 50 kiloparsecs from the center of the galaxy.
Okay, it's right time for our science coffee. So let's thank Annette again, please.